Welcome to Slumbertainment. Get comfortable, close your eyes, and let yourself relax. Tonight we explore the history of rockets. Please like and subscribe for more restful content. Now, let's begin. In the beginning, fire was something to fear. For countless generations, humans watched lightning strike dry grass, saw forests consumed by flame, and learned to respect the raw power of combustion. But eventually, our ancestors did something remarkable. They captured fire, controlled it, and began to wonder what else it might do. This curiosity, this fundamental human impulse to harness the forces of nature, would eventually lead us to the stars. The story of rockets begins not with gleaming spacecraft or complex mathematics, but with something far simpler: the discovery that fire could push. Long before anyone understood the physics of action and reaction, before Newton would articulate his famous laws of motion, people noticed that certain things moved when they burned. A log in a fire might suddenly shift or roll. Burning bamboo, common across ancient Asia, would sometimes explode with startling force, sending fragments flying in unexpected directions. The heat building inside the hollow chambers of bamboo created pressure, and that pressure sought release. When it found an opening, it rushed out violently, and the bamboo moved in the opposite direction. This wasn't magic, it was physics, though no one yet had that word for it. The ancient Chinese were masters of observation. Living in a world rich with bamboo forests, they witnessed these natural explosions countless times. But sometime around the 9th century, during the Tang dynasty, Chinese alchemists made a discovery that would change everything. They were searching for an elixir of immortality, mixing various substances in hopes of creating something that would grant eternal life. Instead, they created something that brought death with unprecedented efficiency. They discovered gunpowder. The recipe was surprisingly simple, though getting the proportions right required experimentation and no small amount of danger. Saltpeter, which could be scraped from cave walls and cellars where it formed naturally, provided oxygen in abundance. Charcoal, the black residue left after burning wood in limited air, supplied carbon for fuel. Sulfur, a yellow mineral found near hot springs and volcanic regions, lowered the ignition temperature and made the mixture more reliable. When combined in the right ratios and ignited, these three substances didn't just burn. They deflagrated, releasing energy so rapidly that the expanding gases could shatter stone, propel projectiles, and eventually lift objects into the sky. At first, gunpowder was used for fireworks and signals. The Chinese had long traditions of celebration and spectacle, and these new pyrotechnic displays added wonder to festivals and ceremonies. But it didn't take long for military minds to recognize the potential. If gunpowder could launch a shower of sparks and colors into the night sky, perhaps it could also launch weapons toward an enemy. The earliest attempts were crude. Packets of gunpowder attached to arrows would sometimes explode prematurely, injuring the archer rather than the target. But gradually, through trial and error, Chinese engineers developed something more sophisticated. They called them fire arrows, though they bore little resemblance to the arrows fired from traditional bows. These devices consisted of a long stick, similar to an arrow shaft, with a tube of gunpowder attached near one end. The tube was sealed at one end and left open at the other. When the gunpowder inside ignited, hot gases rushed out of the open end, and the principle that would later be formalized as Newton's third law went to work. For every action, there is an equal and opposite reaction. The gases pushing backward meant the arrow pushed forward, propelled not by a bowstring, but by the explosive force of combustion. These fire arrows could travel much farther than conventional arrows, and carried the added advantage of starting fires wherever they landed. The earliest reliable records of fire arrows being used in warfare date to the Battle of Kaifeng in the year 1232, during the Jin dynasty's desperate defense against Mongol invaders. The defenders of Kaifeng, facing one of history's most formidable military forces, unleashed these primitive rockets against their attackers. Contemporary accounts describe the sky filled with streaking flames, the sound of explosions echoing across the battlefield, and the terror these weapons inspired among soldiers who had never encountered anything like them. The fire arrows weren't particularly accurate, and their explosive power was modest compared to what would come later, but they represented something entirely new in human warfare. For the first time, humans had created a weapon that could propel itself, that carried its own source of momentum, independent of any bow or catapult. What made these fire arrows truly revolutionary wasn't their immediate military effectiveness, which was limited, but the principle they embodied. They demonstrated that controlled combustion could generate thrust, that fire could be directed and harnessed to create motion. This was rocket propulsion in its most primitive form, and though the Chinese engineers who developed these weapons couldn't have known it, they had discovered the fundamental principle that would eventually carry humans beyond Earth's atmosphere. Over the following centuries, fire arrow technology spread along trade routes and through military conquest. The Mongols, having experienced these weapons firsthand at Kaifeng and other sieges, adopted and refined them. As Mongol armies swept westward, reaching deep into Europe and southward into the Middle East, they brought knowledge of gunpowder weapons with them. Arab engineers studied captured fire arrows and began developing their own versions. By the 13th and 14th centuries, knowledge of rockets had diffused across much of Asia and into Europe, though each culture adapted the technology to their own needs and materials. European accounts from the medieval period describe rockets as exotic curiosities, fearsome weapons from distant lands. The English scholar Roger Bacon, writing in the mid-1300s, recorded a formula for gunpowder that had clearly been adapted from Eastern sources. Italian and German manuscripts from the same era contain illustrations of rocket-like devices, often wildly imaginative and probably non-functional, but indicating a growing fascination with the potential of self-propelled weapons. The fundamental challenge remained consistent across all cultures: how to make the rocket fly straight, how to increase its range, and how to ensure it exploded or ignited at the right moment. Yet for all their promise, early rockets remained unpredictable and dangerous. The gunpowder itself was inconsistent, varying in quality depending on the purity of ingredients and the skill of whoever mixed them. The casings, typically made from bamboo, wood, or paper, often ruptured prematurely. Guidance was essentially non-existent. Once launched, a fire arrow went wherever physics and wind took it. Despite these limitations, the basic concept had been proven. Fire could push. Combustion could create thrust. The rocket, in its most elementary form, had been born. What remained was centuries of refinement, understanding, and ultimately, the vision to see that this technology might carry us not just across battlefields, but across the cosmos itself. The knowledge of rockets, once confined to the courts and battlefields of ancient China, began its slow migration across the medieval world, like seeds carried on unpredictable winds. This dissemination happened not through any single dramatic moment of discovery, but through the gradual accumulation of observations, the capture of weapons in battle, the movement of artisans and engineers between kingdoms, and the translation of technical manuscripts from one language to another. By the 14th and 15th centuries, rockets had become a recognized, if still somewhat mysterious, component of military arsenals across Europe, the Middle East, and Asia. Yet despite their growing familiarity, These devices remained temperamental, dangerous, and only marginally understood. European military engineers approached rockets with a mixture of enthusiasm and frustration. Unlike cannons, which were becoming increasingly sophisticated and reliable during this period, rockets seemed to defy systematic improvement. A cannon was fundamentally simple in concept: a strong metal tube, sealed at one end, that directed an explosion's force behind a projectile. The engineering challenges were substantial, certainly, but they were challenges of metallurgy and precision manufacturing. Rockets presented different problems entirely. They had to carry their propellant with them, maintain stability during flight, and somehow stay pointed in the intended direction despite being pushed from behind by an off-center force. Many early European rockets tumbled end over end, exploded on their launch frames, or traced wild arcs through the sky before landing nowhere near their targets. The Italian engineer Jones de Fontana, working in the early 1400s, produced detailed drawings of rockets that revealed both sophisticated thinking and fundamental misunderstandings. His manuscripts, beautifully illustrated with the precision typical of Renaissance technical drawings, showed rockets with wings, rockets riding on rails, and even fanciful designs for rocket-powered torpedoes that could supposedly travel underwater. Some of his ideas were remarkably prescient. The concept of using guide rails to stabilize a rocket during its initial acceleration would eventually prove crucial. Other ideas reflected the era's incomplete grasp of physics. Water resistance would make underwater rocket propulsion essentially impossible, but Fontana had no way of knowing this. He was working from observation and intuition, not from any comprehensive theory of how rockets actually functioned. What these early engineers lacked was a theoretical framework. They could see that rockets worked, more or less, but they couldn't explain why in any rigorous way. The relationship between the mass of propellant, the speed of exhaust gases, and the resulting thrust remained mysterious. The principles governing stable flight, the role of the center of mass relative to the center of pressure, the physics of combustion itself, all of these would have to wait for later centuries to be properly understood. In the meantime, rocket development proceeded through trial and error, with each generation of weapons makers building incrementally on what had come before. The Indian subcontinent emerged as an unexpected center of rocket innovation during the 17th and 18th centuries. The kingdom of Mysore, in what is now southern India, developed rockets that were substantially more advanced than anything being produced in Europe at the time. These Mysorean rockets used metal tubes instead of the paper or wooden casings common elsewhere, which allowed them to contain much higher pressures without rupturing. Higher pressure meant more thrust, which translated to greater range and more devastating impact. The metal tubes were typically made of soft iron, hammered and welded into cylinders, then attached to bamboo poles that provided stability in flight. The ruler Hyder Ali and his son Tipu Sultan recognized rockets as potentially decisive weapons and invested accordingly. They established dedicated rocket corps within their armies, units of soldiers trained specifically in the deployment and tactical use of rockets. These weren't artillerymen who happened to occasionally use rockets. They were specialists, organized into distinct military formations. By the 1770s and 1780s, Mysore could field thousands of rocket troops in a single engagement, capable of launching sustained barrages that could break cavalry charges and create chaos among enemy formations. British colonial forces encountered Mysorean rockets during the Anglo-Mysore Wars and found them terrifying. Contemporary British accounts describe the night sky filled with streaking fire, the distinctive whooshing sound of rockets in flight, and the psychological impact of weapons that seemed to come from nowhere and everywhere simultaneously. In the Battle of Pollilure in 1780, Mysorean rocket troops helped inflict a devastating defeat on British forces. The rockets themselves caused relatively few direct casualties. Their accuracy remained poor, but they panicked horses, disrupted formations, and created enough confusion for other Mysore forces to exploit. One British officer, wounded and captured during the battle, later wrote about the experience of being under rocket bombardment, describing it as unlike anything he had previously encountered in warfare. The British response was characteristic of imperial military policy: study the enemy's weapons and adopt whatever works. Colonel William Congreve, whose father directed the Royal Laboratory at Woolwich, the British military's main facility for developing ammunition and explosives, took particular interest in captured Mysorean rockets. The younger Congreve conducted extensive experiments, testing different propellant mixtures, casing materials, and stabilization methods. By the early 1800s, he had developed what became known as Congreve rockets, which would see extensive use in the Napoleonic Wars and beyond. Congreve's designs borrowed heavily from the Mysorean rockets, but incorporated improvements based on Britain's more advanced metallurgy and manufacturing capabilities. His rockets ranged in size from small incendiary devices weighing just a few pounds to massive weapons over 3 feet long and weighing more than 30 pounds. The larger versions could reach distances of 2 miles or more under ideal conditions, though ideal conditions rarely existed in actual combat. Accuracy remained the persistent problem. Even the best Congreve rockets scattered widely, making them suitable for bombarding large targets like cities or fortifications, but nearly useless against specific tactical objectives. The bombardment of Copenhagen in 1807 is often cited as the first significant use of Congreve rockets in European warfare. British forces, seeking to prevent the Danish navy from falling into French hands, launched an assault on the city that included thousands of rockets fired from specialized launch vessels. The rockets started numerous fires throughout Copenhagen, and while their military effectiveness was debatable, their psychological impact was undeniable. The randomness of where rockets landed, the impossibility of predicting which building might be struck next, created a particular kind of terror that conventional artillery somehow didn't inspire. American forces would later experience Congreve rockets during the War of 1812, most famously during the British bombardment of Fort McHenry in Baltimore. The fort's defenders endured 25 hours of shelling that included both conventional explosives and rockets. Francis Scott Key, witnessing the bombardment from a ship in the harbour, wrote what would become the American national anthem, and his phrase, "the rocket's red glare," immortalized these weapons in American cultural memory. The fort withstood the assault. The British withdrew, and the battle itself had no decisive strategic impact, but those rockets, arcing through the night sky over Baltimore Harbor, had secured their place in history through poetry as much as through military achievement. Yet for all the attention rockets received, for all the resources invested in their development, they remained fundamentally inferior to conventional artillery throughout most of the 19th century. Cannons were more accurate, more reliable, more powerful, and easier to use. Rockets had exactly one advantage. They could be launched from lightweight platforms that required no heavy gun carriages or elaborate emplacements. This made them useful in certain specific situations, particularly for naval forces or in rough terrain where moving heavy artillery was impractical, but it wasn't enough to make them dominant. As the 19th century progressed and artillery continued improving, military interest in rockets actually declined. They became niche weapons, sometimes used, more often left in storage. The future of rocketry, it seemed, would have to wait for someone to imagine a purpose beyond warfare, a destination beyond the next hill or the next city. That imagination was coming, carried by writers and dreamers who looked up rather than forward, who wondered not about the next battle, but about the next world. While military engineers gradually lost interest in rockets as weapons of war, a different kind of mind began to consider what else these devices might accomplish. Throughout the 19th century, as industrialization transformed the pace and scale of human civilization, a peculiar sort of dreamer emerged. These were people who combined technical knowledge with imaginative vision, who read both engineering journals and adventure stories, who understood mathematics but also gazed at the night sky with wonder. They began asking a question that would have seemed absurd to earlier generations. If rockets could travel through air, pushing themselves forward by expelling hot gases backward, could they perhaps travel where there was no air at all? Could they, in other words, reach space? The idea of travelling beyond Earth's atmosphere had ancient roots. Greek philosophers had speculated about other worlds. Medieval scholars had debated whether the heavens were accessible to mortals. But these discussions had always been purely theoretical, often theological, concerned with what might be possible for divine beings or immortal souls rather than for humans in physical bodies. What changed in the 19th century was the gradual realization, emerging from advances in physics and astronomy, that space wasn't actually that far away. The atmosphere thinned with altitude. Everyone knew this from mountain climbing and balloon flights, and calculations suggested it effectively ended somewhere between 50 and 100 miles up. 100 miles seemed like an enormous distance in everyday terms, but it was trivial compared to the scale of the Earth itself, let alone the distances to the moon or planets. Space, it turned out, was just overhead, tantalizingly close if only something could push hard enough and fast enough to reach it. Jules Verne, the French novelist whose works helped define science fiction as a literary genre, published From the Earth to the Moon in 1865. His story featured a massive cannon that fired a capsule containing 3 adventurers toward the moon. Verne had consulted with scientists and engineers while writing the book, and his calculations, while not perfect, were remarkably sophisticated for their time. He understood that reaching the moon required achieving a specific velocity, approximately 7 miles per second, what we now call escape velocity. He recognized that the passengers would experience tremendous forces during acceleration and would need some method of surviving the crushing pressure. His solution, having them fired from a gun, was actually completely impractical. The acceleration would kill anyone instantly, but the fact that he engaged seriously with the real physics of the problem inspired readers to think about spaceflight not as fantasy, but as an engineering challenge. Among those readers was a shy Russian schoolteacher named Konstantin Tsiolkovsky, born in 1857 in a small village in Ryazan province. Tsiolkovsky had become nearly deaf after suffering scarlet fever as a child, and this isolation from normal social interactions seemed to intensify his inner life. He spent countless hours reading, studying, and thinking. He taught mathematics and physics to support himself, but his real passion was exploring theoretical problems that most of his contemporaries considered pointless daydreaming. What interested Tsiolkovsky more than anything was the question of whether humans could leave Earth, and if so, how they might accomplish this apparently impossible feat. Tsiolkovsky began publishing his ideas in the 1890s, writing papers with titles like Free Space and Dreams of Earth and Sky. His work was largely ignored at first, published in obscure Russian journals that few people read and fewer understood. But Tsiolkovsky was undeterred. He continued developing his theories, working through the mathematics of spaceflight with meticulous care. In 1903, he published what would become his most influential paper, The Exploration of Cosmic Space by Means of Reaction Devices. This dense technical document laid out the fundamental principles of astronautics decades before anyone would build a rocket capable of reaching space. Tsiolkovsky's key insight was understanding that rockets, unlike every other form of transportation humans had developed, didn't depend on pushing against anything external. A car pushes against the road. A boat pushes against water. An airplane pushes against air. But a rocket pushes against itself. Or more precisely, against the propellant it carries and expels. This meant rockets could function in the vacuum of space, where there was nothing to push against except the rocket's own exhaust. This seems obvious in retrospect, but in Tsiolkovsky's era, many educated people believed rockets needed air to push against, just as a swimmer needs water. Tsiolkovsky demonstrated mathematically that the opposite was true. Rockets actually worked better in vacuum because there was no air resistance to slow them down. He also derived what became known as the Tsiolkovsky rocket equation, a deceptively simple mathematical relationship between a rocket's final velocity, the velocity of its exhaust gases, and the ratio between its fully fueled mass and its empty mass. This equation revealed something profound and somewhat depressing about rocket physics. Reaching high velocities required carrying truly enormous amounts of propellant. To reach escape velocity using the chemical propellants available in Tsiolkovsky's time, a rocket would need to be almost entirely fuel, with the actual payload representing just a tiny fraction of the total mass. The numbers were daunting, but they were finite. The equation proved that spaceflight was possible in principle, even if the engineering challenges were formidable. Tsiolkovsky went further, proposing specific solutions to problems that other dreamers hadn't even recognized yet. He described multi-stage rockets, where sections would be discarded as their fuel was exhausted, improving the mass ratio for the remaining stages. He discussed using liquid propellants, which could be controlled more precisely than solid propellants and would allow for much higher performance. He wrote about spinning spacecraft to create artificial gravity, about using solar energy to power systems in space, about establishing permanent settlements beyond Earth. Much of this was highly speculative, but it was speculation grounded in physics and mathematics rather than pure fantasy. Tsiolkovsky was imagining not just that humans might reach space, but how they would actually live and work there. In America, a physicist named Robert Goddard was pursuing similar ideas, though he arrived at them independently and with a somewhat different emphasis. Goddard, born in 1882 in Worcester, Massachusetts, experienced his moment of inspiration on October 19, 1899, while climbing a cherry tree in his family's yard. He later described looking up at the sky and suddenly seeing in his mind a device that could ascend to the planet Mars. This vision, this sudden conviction that spaceflight was not just possible but achievable, would drive the rest of his life's work. Goddard was more experimentally minded than Tsiolkovsky, less interested in theoretical papers than in building actual hardware. He conducted careful tests of different propellants, nozzle designs, and ignition systems. He developed methods for pumping liquid fuels into combustion chambers, for stabilizing rockets in flight, for measuring thrust and performance. This work was tedious, repetitive, often frustrating, and occasionally dangerous. Small explosions were common in Goddard's laboratory, and he accumulated burns and injuries as he refined his designs through hundreds of small failures. In 1919, Goddard published a monograph titled A Method of Reaching Extreme Altitudes, which outlined his research and suggested, in carefully worded language, that rockets might someday reach the moon. The press seized on this idea and ridiculed it mercilessly. The New York Times published an editorial mocking Goddard's apparent ignorance of basic physics, claiming that everyone knew rockets couldn't function in vacuum because there was no air to push against. This was exactly the misconception Tsiolkovsky had addressed years earlier, but the Times editors hadn't read Tsiolkovsky. The ridicule stung Goddard deeply, and he became increasingly secretive about his work, reluctant to share his findings until he had achieved undeniable success. That success came, in a modest way, on March 16, 1926, on a farm in Auburn, Massachusetts. Goddard launched the world's first liquid-fueled rocket. It was a spindly, awkward-looking device, just over 10 feet tall, burning gasoline and liquid oxygen. The flight lasted only 2.5 seconds, reached an altitude of 41 feet, and travelled 184 feet before crashing into a frozen cabbage patch. By any reasonable standard, it was an underwhelming achievement, barely more impressive than a good firework. But principles had been proven. A liquid-fueled rocket could be built, ignited and controlled. The flame could be sustained. The vehicle could lift itself. The vision that Tsiolkovsky had outlined, mathematically, that Goddard had dreamed about in his cherry tree 27 years earlier, had taken physical form, however briefly and modestly. The age of spaceflight had begun, though it would be decades before anyone recognized that cold March day as the beginning of anything at all. While Goddard worked in increasing isolation on his farm in Massachusetts, conducting experiments he shared with almost no one, a very different approach to rocketry was developing in Germany. There, enthusiasm for spaceflight had captured the imagination not of solitary inventors, but of entire societies of amateurs, students, and engineers who gathered to share ideas, conduct experiments, and dream collectively about reaching the stars. This collaborative spirit, so unlike Goddard's secretive methods, would accelerate rocket development in ways that no individual working alone could match. The German fascination with rockets and space travel owed much to a single book. In 1923, a Transylvanian-born engineer named Hermann Oberth published The Rocket into Planetary Space, a technical treatise that combined rigorous mathematics with visionary proposals. Oberth had independently derived many of the same principles that Tsiolkovsky had worked out decades earlier, and he added his own insights about guidance systems, life support, and mission design. Unlike Tsiolkovsky's papers, which languished in obscure Russian journals, Oberth's book appeared at exactly the right moment, in exactly the right place. Post-war Germany was hungry for something to believe in, some vision of a future beyond the humiliation of defeat and the grinding poverty of the early 1920s. The idea of spaceflight, of German engineering reaching beyond Earth itself, provided that vision. Amateur rocket clubs began forming throughout Germany. University students built crude rockets and launched them from vacant fields, often to the alarm of local authorities. The most significant of these groups was the Verein für Raumschifffahrt, the Society for Space Travel, founded in 1927. The VFR attracted an eclectic membership that included engineers, students, science fiction writers, and enthusiasts with no technical background but endless enthusiasm. They published journals, held public lectures, and most importantly, conducted actual experiments. They established a testing ground they called the Raketenflugplatz, the rocket flight place on the outskirts of Berlin, where members could build and launch their designs. Among the VFR's most dedicated members was a young aristocrat named Werner von Braun. Born in 1912 to a wealthy Prussian family, von Braun had become obsessed with spaceflight after reading Oberth's book as a teenager. He joined the VFR while still a student and quickly distinguished himself with his technical abilities and his talent for organising and leading teams. Von Braun was charming, ambitious, and utterly convinced that humans would reach space within his lifetime. He was also willing to work with anyone who could provide resources for rocket development, a flexibility that would later prove both enabling and morally compromising. The VFR's experiments yielded increasingly sophisticated rockets through the early 1930s. Their designs used liquid oxygen and alcohol or gasoline, following the path Goddard had pioneered, but developing it further through systematic testing and modification. They experimented with different combustion chamber geometries, cooling systems, and guidance mechanisms. Some rockets exploded spectacularly. Others flew successfully, reaching altitudes of several thousand feet. Each test provided data, and the accumulated data gradually revealed what worked and what didn't. This promising work caught the attention of the German military. The Treaty of Versailles, imposed after World War I, had strictly limited German artillery and conventional weapons, but it said nothing about rockets, which nobody had thought to ban. The German army saw an opportunity. If rockets could be developed into weapons, they might provide a way to circumvent the treaty's restrictions. In 1932, the army invited von Braun and other VFR members to demonstrate their rockets at a military testing ground. The demonstration went well, and the army offered von Braun a position developing rockets for military use. He accepted without apparent hesitation. Von Braun's decision marked a turning point. Rocket development, which had been primarily the domain of dreamers and hobbyists, became a military project with substantial funding and resources. The work moved from the public Raketenflugplatz to the secret military facility at Kummersdorf, and later to the massive complex at Peenemünde on the Baltic coast. Hundreds of engineers, technicians and scientists were eventually employed there, working on what would become the V-2 rocket, the Vergeltungswaffe 2, or Vengeance Weapon 2. The V-2 was a remarkable machine, far more sophisticated than anything Goddard or the early VFR had built. It stood 46 feet tall, weighed nearly 14 tons when fueled, and could carry a 1-ton warhead more than 200 miles. It burned liquid oxygen and ethanol, the same basic propellants the VFR had used, but in far larger quantities and at much higher pressures. The V-2's engine produced roughly 56,000 pounds of thrust, enough to push the fully fueled rocket to speeds exceeding 3,000 miles per hour. At the peak of its trajectory, the V-2 reached altitudes above 60 miles, briefly touching the edge of space before arcing downward toward its target. Technically, the V-2 was a triumph. It was the first long-range guided missile, the first human-made object to reach space, and a demonstration that rockets could be not just experimental curiosities, but practical, functional machines. The engineering challenges von Braun's team had overcome were immense. They had developed turbopumps that could reliably deliver tons of propellant per minute into the combustion chamber. They had solved the cooling problems that had plagued earlier rockets by circulating alcohol through channels in the combustion chamber walls. They had created a guidance system using gyroscopes and graphite vanes in the exhaust stream to control the rocket's orientation. Every aspect of the V-2 represented cutting-edge technology, much of it invented specifically for this project. Morally, the V-2 was an atrocity. More than 3,000 V-2 rockets were launched against Allied cities, primarily London and Antwerp, between September 1944 and March 1945. Each arrived without warning, faster than sound, impossible to intercept. The explosions killed approximately 9,000 people and injured many thousands more. But the human cost of the V-2 extended far beyond the casualties caused by the explosions. The rockets were built primarily by slave labourers, prisoners from concentration camps who worked under horrific conditions in underground factories. More people died building the V-2 than were killed by the rockets themselves. Estimates suggest that at least 20,000 prisoners died from exhaustion, starvation, disease, and brutal mistreatment while manufacturing the missiles that von Braun and his team designed. Von Braun later claimed ignorance of these conditions, or at least tried to distance himself from responsibility for them. The historical record suggests otherwise. He visited the underground factories. He selected workers. He was deeply embedded in a system that relied on slave labour, and he continued his work knowing how the rockets were being produced. His complicity in these crimes would haunt his later reputation, though it did not prevent his subsequent career. As the war ended and Germany faced defeat, von Braun and his team made careful calculations about their future. They could surrender to the advancing Soviet forces from the east, or to the Americans and British approaching from the west. Von Braun chose the Americans, believing they would offer better treatment and more resources for continuing his work. In early May 1945, von Braun and approximately 125 of his top engineers surrendered to American forces. The Americans also captured hundreds of partially assembled V-2 rockets and vast quantities of documentation. The Soviets, arriving at Peenemünde shortly afterward, found what remained: lower-level technicians, scattered equipment, and enough information to begin their own rocket program. The V-2, developed as a weapon, would become the foundation for the space programs of both superpowers. The dreams of Tsiolkovsky and Oberth, the experiments of Goddard and the VFR enthusiasts, had led through moral compromise and wartime horror to machines that could finally touch space. What came next would determine whether that capability served exploration or destruction. The end of World War II left the world divided into competing spheres of influence, with the United States and the Soviet Union emerging as superpowers locked in ideological confrontation. This Cold War, as it came to be called, would be fought through proxy conflicts, espionage, propaganda, and technological competition. And nothing captured the technological dimension of this rivalry more dramatically than rockets. Both nations recognized that the same machines capable of delivering payloads into space could also deliver nuclear weapons across continents. The rocket, which visionaries had imagined as humanity's vehicle to the stars, became first and foremost an instrument of potential annihilation. The Americans moved quickly to exploit their capture of German rocket technology and personnel. Von Braun and his colleagues were brought to the United States through Operation Paperclip, a program designed to recruit German scientists before the Soviets could claim them. The moral implications of bringing former Nazi collaborators into America and giving them influential positions was swept aside in favor of strategic necessity. Von Braun was sent to Fort Bliss in Texas, where he and his team began training American military personnel in rocket technology and conducting test launches of captured V-2 rockets at the nearby White Sands Proving Ground in New Mexico. These early American launches were essentially educational exercises. The V-2 rockets were relics from the war, and while they provided valuable experience, they represented yesterday's technology. What America needed was its own rocket program, designed and built domestically. But rocket development was expensive, and in the immediate post-war years, military budgets were shrinking as the nation demobilized. Progress was modest, incremental, focused primarily on military applications rather than any grand vision of space exploration. The Soviet Union took a different approach. Stalin recognized that rockets represented a potential way to offset America's advantage in long-range bombers, which could deliver nuclear weapons deep into Soviet territory, while Soviet aircraft lacked the range to strike back effectively. The Soviet leadership gave rocket development high priority and devoted substantial resources to it. They had captured some German equipment and personnel from Peenemünde, though not the senior leadership that had surrendered to the Americans. What they lacked in German expertise, they compensated for with talented Soviet engineers who had been developing rockets independently even before the war. Chief among these was Sergei Korolev, an engineer whose life story embodied both the promise and the brutality of the Soviet system. Born in 1906 in Ukraine, Korolev had become fascinated with aviation and rocketry as a young man. He joined the Soviet Rocket Research Group in the 1930s and worked on early liquid-fueled rocket designs. Then, in 1938, during Stalin's Great Purge, Korolev was arrested on fabricated charges of sabotage and treason. He was tortured, his jaw was broken during interrogation, and he was sentenced to 10 years in the Gulag. He spent months in gold mines in the Arctic, where prisoners died regularly from cold, exhaustion, and starvation. Only the intervention of influential colleagues who argued that his engineering expertise was too valuable to waste saved him from death. He was transferred to a special prison where technical professionals were forced to work on military projects while remaining incarcerated. Korolev was eventually released in 1944, his health permanently damaged, but his determination intact. After the war, he was appointed chief designer of the Soviet ballistic missile program, a position that gave him enormous authority but also enormous pressure. Stalin demanded results, and failure could mean a return to the Gulag or worse. Korolev worked with ruthless efficiency, driving his team to master and then exceed the German V-2 technology. By the early 1950s, the Soviet Union had developed the R-7, a massive rocket far more powerful than anything America possessed. The R-7 was designed primarily as an intercontinental ballistic missile, capable of carrying a nuclear warhead from the Soviet Union to the United States. It was a monster of a machine, standing more than 90 feet tall and using 4 strap-on boosters clustered around a central core, all burning together at liftoff to produce approximately 1 million pounds of thrust. The engineering was relatively crude compared to what would come later, but it was effective, and crucially, it was powerful enough not just to loft warheads across continents, but potentially to place objects into orbit around Earth. Korolev understood this. While he worked on military projects because that was what Stalin and later Khrushchev demanded, his personal passion remained space exploration. He saw the R-7 not just as a weapon, but as a potential launch vehicle for satellites and eventually for human spaceflight. He began advocating for permission to attempt launching a satellite, arguing that it would demonstrate Soviet technological superiority and provide propaganda value. The Soviet leadership was initially skeptical, but eventually approved a modest satellite program. The satellite Korolev's team designed was remarkably simple, almost crude. It was a polished metal sphere, just 23 inches in diameter, weighing 184 pounds. Inside were batteries, a radio transmitter, and basic instruments to measure temperature and pressure. The sphere had 4 external antennas that trailed behind it. That was it. No cameras, no scientific instruments of any sophistication, just enough equipment to broadcast a simple beeping signal that anyone with a radio receiver could detect. They called it Sputnik, a Russian word that translates roughly as travelling companion or fellow traveller. On October 4th, 1957, an R-7 rocket lifted off from the Baikonur Cosmodrome in Kazakhstan, carrying Sputnik toward orbit. The launch was flawless. The rocket's engines burned as designed, the stages separated cleanly, and 98 minutes after launch, Sputnik completed its first orbit of Earth, circling the planet every 96 minutes and broadcasting its distinctive beeping signal. That signal, when picked up by radio operators around the world, announced that humanity had entered a new era. for the first time a human-made object was orbiting Earth. The space age had officially begun. The impact of Sputnik on American society was profound and immediate. The United States had considered itself the world's technological leader, and suddenly the Soviet Union had achieved something America had not. The beeping signal from space, which anyone could hear, was a constant reminder of Soviet achievement and, by implication, American inadequacy. Politicians demanded explanations. Why had America fallen behind? What did this mean for national security? If the Soviets could place a satellite in orbit, they could certainly place a nuclear warhead anywhere on American soil. Sputnik transformed from a scientific achievement into a symbol of Cold War competition. The American response combined panic, determination, and institutional reorganization. President Eisenhower, who had actually known about the Sputnik program through intelligence reports and hadn't considered it particularly threatening, found himself forced to respond to public anxiety. Funding for American rocket and satellite programs increased dramatically. Science education became a national priority, with new emphasis on mathematics and physics in schools. And within months, America created the National Aeronautics and Space Administration, NASA, to coordinate and accelerate the nation's space efforts. The Soviets, meanwhile, were celebrating their triumph and planning their next demonstration. Just 1 month after Sputnik, on November 3rd, 1957, they launched Sputnik 2. This satellite was far more ambitious than the first. It weighed over 1,000 pounds and carried a passenger, a dog named Laika. The flight was intended to test whether a living creature could survive launch and orbital conditions, crucial information if humans were eventually to follow. Laika survived the launch and the initial hours in orbit, but the spacecraft's life support system failed, and she died within hours from overheating and stress. The Soviets initially reported that Laika had lived for several days before being painlessly euthanized, but the truth emerged decades later. Still, the mission demonstrated that living things could survive launch and at least briefly endure the conditions of spaceflight. The era of hesitant, modest rocket experiments was over. Both superpowers were now locked in a race to demonstrate technological and ideological superiority through achievements in space. The stakes were enormous, the resources committed were unprecedented, and the pace of progress would accelerate beyond anything the early pioneers could have imagined. Tsiolkovsky's theories, Goddard's experiments, and von Braun's engineering had converged into a geopolitical competition that would drive humanity off the surface of its home planet. The question was no longer whether humans would reach space, but when, and which nation would get there first. The years following Sputnik witnessed an escalating competition between the Soviet Union and the United States, each nation striving to demonstrate superiority through increasingly ambitious achievements in space. What had begun as a technological race quickly became something more profound, a contest over which system, capitalism or communism, represented humanity's future. Every satellite launch, every mission milestone, every success or failure carried meaning beyond its immediate technical accomplishment. America's first attempts to match the Soviet achievement met with embarrassing failure. On December 6, 1957, a Vanguard rocket carrying America's first satellite attempt exploded on the launch pad in front of live television cameras and assembled journalists. The rocket rose perhaps 4 feet before its engines failed, and it collapsed back onto the pad in a spectacular fireball. Newspapers mockingly dubbed it Kaputnik and Flopnik. The humiliation was complete when the tiny satellite, thrown clear by the explosion, lay in the sand nearby, still transmitting its pathetic beeping signal. Success finally came on January 31st, 1958, when a Jupiter C rocket, developed by von Braun's team, successfully placed Explorer 1 into orbit. The satellite was small, weighing just over 30 pounds, but it carried instruments designed by physicist James Van Allen that made a genuine scientific discovery. The satellite's radiation detectors revealed belts of charged particles trapped by Earth's magnetic field, regions now known as the Van Allen belts. This discovery reminded everyone that space exploration could yield real scientific knowledge, not just propaganda victories. But the Soviets maintained their lead through a series of impressive firsts. Their rockets were more powerful, their satellites larger, and their willingness to take risks greater. In September 1959, Luna 2 became the first human-made object to reach another celestial body when it crashed into the Moon's surface. The following month, Luna 3 swung around the far side of the Moon and transmitted the first photographs of the lunar surface never visible from Earth, revealing a landscape heavily cratered and remarkably different from the near side. These achievements set the stage for the ultimate demonstration, putting a human being into space. Both nations understood that whoever accomplished this first would claim a victory of immense symbolic importance. The satellite was impressive, but it was still just a machine. A living person orbiting Earth would represent something qualitatively different, a statement that humans were no longer bound to their planet. The Soviets moved first. On April 12, 1961, a rocket lifted off from Baikonur carrying Vostok 1, and inside that spacecraft was Yuri Gagarin, a 27-year-old Soviet Air Force pilot. Gagarin's flight lasted 108 minutes, a single orbit of Earth, before he safely returned. His famous statement upon seeing Earth from space, "The Earth is blue," became one of the most quoted phrases of the 20th century. The flight was risky, the technology barely tested, but it worked. Gagarin became an instant global celebrity, and the Soviet Union had scored another propaganda triumph. America's response came less than a month later. On May 5, 1961, astronaut Alan Shepard rode a Mercury capsule atop a Redstone rocket for a 15-minute suborbital flight. It wasn't an orbital mission. Shepard reached space but came right back down without circling Earth. But it demonstrated that America was in the race. President Kennedy, watching these events unfold and recognizing the geopolitical stakes, made a bold decision. On May 25, 1961, he addressed Congress and announced that America would land a man on the Moon and return him safely to Earth before the decade's end. Kennedy's announcement was audacious. America hadn't yet achieved an orbital flight, had barely managed 15 minutes in space, and now the president was committing to landing on the Moon within 9 years. The technology didn't exist. The rockets weren't built. Many of the problems hadn't even been identified yet, let alone solved. But Kennedy understood that such an ambitious goal would focus national effort, provide clear direction, and offer a metric for success that was unambiguous. Either America would reach the Moon by the deadline, or it wouldn't. The Apollo program that emerged from Kennedy's challenge represented an engineering effort on a scale rarely seen outside of wartime. At its peak, Apollo employed over 400,000 people across thousands of contractors and universities. The budget consumed more than 4% of the federal budget, equivalent to roughly $200 billion in today's currency. NASA constructed massive new facilities. The Kennedy Space Center in Florida, with its enormous vehicle assembly building, mission control in Houston, rocket testing facilities in Mississippi and Louisiana. The centerpiece of Apollo was the Saturn V rocket, the most powerful machine ever to fly successfully. It stood 363 feet tall, taller than a 30-story building, and fully fueled weighed over 6 million pounds. Its first stage alone, burning kerosene and liquid oxygen, produced 7.5 million pounds of thrust through 5 massive engines. The engineering challenges were immense. Materials had to withstand temperatures ranging from the cryogenic cold of liquid oxygen to the searing heat of combustion. Pumps had to move tons of propellant per second. Every component had to work perfectly because a single failure could destroy the entire vehicle and kill the crew. Von Braun led the Saturn V's development, finally achieving his lifelong dream of building rockets for space exploration rather than weapons. The first stage engines were marvels of engineering, each producing more thrust than the entire V2 rocket von Braun had designed during the war. The complete Saturn V, when launched, shook the ground for miles around, producing sounds so intense that observers had to be positioned more than 3 miles away to avoid potential injury from the acoustic energy. Meanwhile, astronauts trained for missions that would push human capabilities to their limits. They practiced in simulators, learned geology, studied spacecraft systems, and prepared for every possible contingency. The training was exhausting and the risks undeniable. In January 1967, 3 astronauts, Gus Grissom, Ed White, and Roger Chaffee, died when fire swept through their Apollo capsule during a ground test. The tragedy forced a complete redesign of the spacecraft and sobering recognition that space exploration was genuinely dangerous. The Soviets, watching America's massive investment in Apollo, faced difficult choices. They lacked the resources to match Apollo directly, and their own lunar program suffered from political infighting, inadequate funding, and technical problems. Korolev died unexpectedly in 1966 during routine surgery, and the Soviet space program lost its most effective leader. Their lunar rocket, the N-1, failed in every test launch, never successfully reaching orbit. The Soviet Union would never seriously threaten America's goal of reaching the moon first, though this only became clear in retrospect. By late 1968, Apollo was ready. The rockets worked, the spacecraft had been redesigned and tested, and the astronauts were prepared. The stage was set for humanity's greatest adventure, the journey to another world. The final approach to the moon began not with a single mission, but with a carefully orchestrated sequence of flights, each one testing systems and procedures essential for the ultimate landing. NASA's methodical approach reflected both the complexity of the challenge and the awareness that failure could mean not just the loss of equipment, but the death of astronauts. Every step had to be proven before the next could be attempted, and every flight carried risks that even the most thorough preparation couldn't entirely eliminate. Apollo 7, launched in October 1968, tested the redesigned command module in Earth orbit. The crew spent 11 days in space, checking systems, practicing maneuvers, and demonstrating that the spacecraft could function reliably. It was an essential but unglamorous mission, a necessary foundation for what would follow. Apollo 8, however, was anything but unglamorous. Launched in December 1968, it carried 3 astronauts completely around the moon, the first humans to leave Earth orbit and venture into deep space. On Christmas Eve, as the spacecraft emerged from behind the moon, the crew broadcast live television pictures of the lunar surface passing below and the Earth rising above the moon's horizon. That image of Earth, a delicate blue and white sphere hanging in the blackness of space, became one of the most influential photographs ever taken, crystallizing humanity's first glimpse of home from another world. Apollo 9 and Apollo 10 followed, each testing additional systems. Apollo 9 tested the lunar module in Earth orbit, proving that the spindly, fragile-looking spacecraft designed to land on the moon could actually fly. Apollo 10 took the lunar module to the moon itself. descending to within 9 miles of the surface before returning to orbit, a full dress rehearsal for landing, except for the final descent. Everything worked. The hardware was ready, the procedures validated, and the crew selected for Apollo 11 prepared for the mission that would attempt what Kennedy had promised 8 years earlier. Neil Armstrong, Buzz Aldrin, and Michael Collins launched from Kennedy Space Center on July 16, 1969, atop a Saturn V rocket. The launch, witnessed by over 1 million people gathered along Florida's coast and watched by hundreds of millions more on television worldwide, proceeded flawlessly. 3 days later, the spacecraft entered lunar orbit. Collins remained in the command module Columbia, while Armstrong and Aldrin transferred to the lunar module Eagle and began their descent. The landing was far from smooth. As Eagle descended, alarms sounded in the cockpit, warning that the computer was overloaded with tasks. Armstrong and Aldrin, trained to handle emergencies, continued the descent while Mission Control frantically analysed the problem. The alarms, it turned out, were caused by a radar switch left in the wrong position, creating unnecessary data processing demands. The computer was prioritising correctly, focusing on critical guidance tasks and postponing less important functions. The landing could continue. But as Eagle dropped toward the surface, Armstrong realised they were heading for a boulder field, a crater filled with rocks that could topple the lander or damage its delicate legs. With fuel running low and seconds to make a decision, Armstrong took manual control and flew the spacecraft horizontally, searching for a smoother landing spot. The fuel gauge dropped toward empty. Mission Control called out the remaining seconds of fuel. Armstrong remained calm, focused entirely on finding safe ground. Finally, with perhaps 20 seconds of fuel remaining, he set Eagle down on the lunar surface. Armstrong's transmission to Earth became one of history's most famous announcements. The Eagle has landed. In Mission Control, controllers who had been holding their breath erupted in cheers. Around the world, people who had been watching tensely relaxed. Humanity had reached another world. Several hours later, after checking systems and preparing equipment, Armstrong opened Eagle's hatch and climbed down the ladder. At the bottom rung, he stepped off onto the lunar surface and spoke words he had carefully considered. That's one small step for man, one giant leap for mankind. The static-filled transmission omitted the article A before man, slightly garbling the intended meaning, but the significance was unmistakable. A human being was walking on the moon. Aldrin joined Armstrong shortly afterward, describing the lunar landscape as magnificent desolation. The two astronauts spent 2.5 hours outside, deploying experiments, collecting rock samples, and planting an American flag. The flag, made of ordinary nylon, had a horizontal rod sewn along the top edge to hold it extended in the airless lunar environment. The astronauts struggled to drive the pole deep enough into the hard lunar soil to keep it upright, and later, when Eagle's ascent engine fired for the return to orbit, the exhaust knocked the flag over. But in that moment, photographed extensively and broadcast worldwide, it served its symbolic purpose. The technical achievements of Apollo 11 were remarkable. The spacecraft had travelled nearly 250,000 miles, navigated to a precise location on another world, landed safely despite computer alarms and navigation challenges, and would soon return its crew safely to Earth. But the mission's impact transcended technology. For the first time, humans had visited another celestial body. The moon, which had hung in Earth's sky since before humans existed, inspiring myths, guiding navigation, marking time, had been touched by human hands. 5 more Apollo missions would successfully land on the moon between 1969 and 1972. Each mission ventured farther from the landing site, stayed longer, and conducted more sophisticated scientific investigations. The later missions carried the Lunar Roving Vehicle, an electric car that allowed astronauts to travel miles from their landing sites. They deployed increasingly complex experiments and brought back hundreds of pounds of lunar rocks and soil that geologists would study for decades. Apollo 17, the final mission, launched in December 1972. Commander Eugene Cernan and geologist Harrison Schmitt spent 3 days on the surface, conducting 3 lengthy excursions and collecting samples from the Taurus-Littrow Valley. As Cernan climbed back into the lunar module for the last time, he spoke a farewell that acknowledged the end of an era. "We leave as we came, and God willing as we shall return, with peace and hope for all mankind." But humanity did not return. Apollo 17 was the last time humans travelled beyond low Earth orbit. The remaining planned Apollo missions were cancelled as budgets tightened and public interest waned. The Moon, so recently within reach, became once again a distant destination. The dreams that had driven Tsiolkovsky and Goddard, that had motivated Kennedy's challenge and NASA's enormous effort, had been realised, but only briefly. The infrastructure built to reach the Moon, the Saturn V rockets and the Apollo spacecraft, would be retired, their manufacturing lines shut down, their engineering knowledge gradually dispersed as teams disbanded and moved on to other projects. The space age, which had begun with such dramatic momentum, with Sputnik and Gagarin and Apollo, entered a new phase characterized not by bold exploration, but by more modest, practical goals. The focus shifted from reaching new destinations to establishing permanent presence in low Earth orbit, from competing for prestige to cooperating on shared projects. The era of the moon landings was over, but the era of living and working in space was just beginning. The years following the Apollo program marked a profound shift in how nations approached spaceflight. The dramatic race to the moon had been driven by geopolitical competition and national pride, but sustaining such efforts proved difficult once the primary goal had been achieved. The enormous costs, the waning public interest, and the absence of clear strategic objectives led both superpowers to reconsider their priorities. Rather than planning ever more ambitious missions to distant destinations, attention turned towards a more pragmatic question. Could humans live and work in space for extended periods? And if so, what could they accomplish there? The Soviet Union had never seriously competed in the race to land on the moon, but they had invested heavily in a different approach to spaceflight. Their focus was on space stations, orbiting laboratories, where cosmonauts could spend weeks or months conducting experiments and learning how the human body adapted to prolonged weightlessness. This emphasis on long-duration missions reflected both practical constraints and strategic vision. The Soviets lacked the resources to match Apollo, but they could build on their experience with increasingly sophisticated orbital missions. The first space station, Salyut 1, was launched in April 1971. It was a relatively modest facility, a single pressurized module about 60 feet long, equipped with living quarters, scientific instruments, and docking ports for visiting spacecraft. The station's first crew tragically died during their return to Earth when a valve accidentally opened, depressurizing their capsule. But subsequent crews successfully occupied Salyut 1 for weeks at a time, establishing routines for daily life in orbit and conducting experiments impossible on Earth. Over the following decade, the Soviet Union launched a series of Salyut stations, each one more capable than the last. Cosmonauts gradually extended their time in space, first to weeks, then to months. They learned to exercise extensively to counteract muscle and bone loss caused by weightlessness. They adapted to sleeping in bags attached to walls, to eating rehydrated food, to the peculiar sensations of floating. They discovered that the human body was remarkably adaptable, but required constant attention to remain healthy in an environment for which evolution had not prepared it. The United States, meanwhile, developed its own space station program. Skylab, launched in May 1973 using a converted Saturn V third stage, was far larger than any Soviet station. Its interior volume was enormous compared to earlier spacecraft, providing room for extensive exercise equipment, scientific instruments, and even a certain degree of privacy for the crew. 3 separate crews visited Skylab over the course of 9 months, with the final mission lasting 84 days. Astronauts conducted solar observations, Earth photography, materials science experiments, and medical studies documenting how their bodies changed during extended weightlessness. Skylab demonstrated that humans could indeed live comfortably in space for months at a time, but it also revealed challenges. The station suffered technical problems from the start when its thermal shield tore away during launch, requiring the first crew to conduct a risky spacewalk to deploy a replacement. Systems broke down, requiring improvised repairs with whatever materials were available. When the final crew departed in February 1974, Skylab was left unoccupied. Plans to refurbish it using the space shuttle, then under development, never materialized. The station gradually lost altitude due to atmospheric drag and re-entered the atmosphere in July 1979, scattering debris across the Australian outback. The space shuttle represented America's vision for making spaceflight routine and economical. Unlike the Apollo capsules, which could be used only once, the shuttle was designed to launch like a rocket but land like an airplane and be refurbished for multiple missions. Proponents argued this reusability would dramatically reduce costs and allow frequent flights carrying satellites, scientific instruments, and eventually commercial payloads. The vision was compelling. A fleet of orbital trucks launching weekly, making space accessible to researchers, businesses, and eventually ordinary people. Reality proved far more complicated. The shuttle was an extraordinarily complex machine, requiring extensive maintenance between flights. Columbia, the first operational orbiter, launched in April 1981 with astronauts John Young and Robert Crippen aboard. The mission was a dramatic success, demonstrating that the shuttle could reach orbit and return safely. But the hoped-for frequent flights never materialized. Each shuttle required months of inspection and refurbishment between missions. Costs remained stubbornly high, and the vehicle's complexity created vulnerabilities that would eventually prove catastrophic. The Soviets, watching America develop the shuttle, continued refining their space station program. In February 1986, they launched Mir, a station designed to grow over time through the addition of specialized modules. Unlike previous stations, which were single units, Mir could be expanded, with new sections added to provide laboratory space, additional docking ports, and living quarters. Over the following decade, Mir grew into a complex facility where cosmonauts routinely spent 6 months or more, and where international cooperation gradually replaced Cold War competition. Mir's longevity and adaptability made it a triumph of incremental engineering. Individual modules launched years apart were successfully connected in orbit. Systems failed and were repaired or replaced. The station survived collisions, fires, and computer failures that would have doomed less robust designs. Cosmonauts became expert at improvisation, fixing broken equipment with spare parts, duct tape, and ingenuity. Mir wasn't elegant or pristine. It became increasingly cluttered and worn over its 15 years of operation, but it functioned, providing continuous human presence in space longer than any previous facility. The experience gained aboard Soviet space stations and aboard Skylab revealed fundamental truths about long-duration spaceflight. Humans could survive and work in weightlessness for extended periods, but not without cost. Bones lost density, muscles atrophied despite exercise, cardiovascular systems adapted to the absence of gravity in ways that made returning to Earth difficult. Vision changed as fluid distribution in the body shifted, increasing pressure around the optic nerve. Psychological challenges emerged from isolation, confinement, and separation from Earth. These weren't insurmountable problems, but they were real constraints that any future deep space mission would need to address. By the late 1980s, the Cold War tensions that had driven the space race were beginning to ease. The Soviet Union, struggling economically, could no longer sustain the expense of competing with American space efforts. The United States, having proved its technological superiority through Apollo and developed the shuttle, had less incentive to treat spaceflight as primarily a geopolitical competition. Conversations began about cooperation, about sharing costs and expertise, about working together rather than in opposition. The space stations, which had been symbols of national achievement, were becoming platforms for international collaboration. The era of space exploration as an extension of earthly conflicts was gradually giving way to something different, though what exactly that would be remained uncertain. The rockets that had carried humans to orbit and to the moon had proved their capability, but their purpose was evolving, shaped less by competition between superpowers and more by the practical realities of operating in an environment that remained profoundly challenging and expensive to reach. As the 1990s began, the geopolitical landscape that had shaped space exploration for decades underwent dramatic transformation. The Soviet Union, weakened by economic stagnation and internal pressures, collapsed in 1991. The Cold War ended not with military confrontation, but with the dissolution of one of the world's two superpowers. This watershed moment had profound implications for spaceflight. The competition that had driven both nations to extraordinary expenditures and ambitious achievements suddenly evaporated, replaced by uncertainty about what would motivate continued investment in space programs. Russia, inheriting the Soviet space program, faced severe financial constraints. Maintaining Mir and continuing to launch crews required resources that the struggling Russian economy could barely provide. The United States, meanwhile, found itself without a clear rival to compete against, making it harder to justify large space budgets to a public and Congress that increasingly questioned the value of expensive programs with no obvious strategic purpose. Yet both nations had accumulated decades of expertise, extensive infrastructure, and workforce whose skills would dissipate if not employed. The solution emerged gradually. Cooperation. The idea of Americans and Russians working together in space would have been nearly unthinkable during the height of the Cold War, but by the mid-1990s it had become not just possible, but necessary. The Shuttle Mir program, beginning in 1994, saw American shuttles docking with the Russian space station, exchanging crews and delivering supplies. American astronauts lived aboard Mir for months at a time, learning from Russian experience with long-duration spaceflight. Russian cosmonauts flew aboard American shuttles. The cooperation was sometimes awkward, complicated by language barriers, different organizational cultures, and lingering suspicions, but it worked. This collaboration laid groundwork for a far more ambitious project. In 1993, plans were announced for the International Space Station, a facility that would dwarf Mir and involve not just Russia and America, but also Canada, Japan, and numerous European nations. The ISS would be assembled gradually over more than a decade, with components launched by both American shuttles and Russian rockets, then connected in orbit by astronauts and cosmonauts working together. It represented an engineering challenge of unprecedented complexity, requiring coordination across multiple space agencies in different languages, with components built on different continents all designed to fit together perfectly in the harsh environment of space. The first ISS component, the Russian-built Zarya module, reached orbit in November 1998. 2 weeks later, the Space Shuttle Endeavour delivered Unity, an American-built connecting node, and astronauts performed the first assembly operation, joining the two modules together in orbit. Over the following years, additional modules arrived one by one: living quarters, laboratories, solar panel arrays, robotic arms, and docking ports. Each addition required careful choreography, with shuttle missions delivering components and crews conducting numerous spacewalks to make connections, route cables, and activate systems. The assembly process revealed both the capabilities and limitations of the space shuttle. The orbiter could carry large, heavy payloads and provide a shirt-sleeve environment where astronauts could work comfortably while manipulating cargo with the robotic arm. But the shuttle was expensive to operate, required months of preparation between flights, and carried risks that became tragically apparent in February 2003 when Columbia disintegrated during re-entry, killing all 7 crew members. The disaster occurred when foam insulation broke away from the external tank during launch and damaged the orbiter's heat shield. The damage went undetected, and when Columbia re-entered the atmosphere, superheated gas penetrated the wing structure, causing catastrophic failure. Columbia's loss marked the second shuttle destroyed in flight, following Challenger's explosion shortly after launch in January 1986. 14 astronauts had died in these 2 accidents, and the investigation following Columbia's destruction revealed that many of the problems identified after Challenger had never been adequately addressed. The shuttle fleet was grounded for over 2 years, while NASA implemented safety improvements. When flights resumed, the remaining orbiters were dedicated primarily to completing ISS assembly before the fleet's planned retirement. The dream of routine, economical access to space that had motivated the shuttle's development remained unfulfilled. Yet despite the shuttle's limitations and tragedies, the ISS gradually took shape. By 2011, when the final shuttle mission delivered equipment and supplies, the station had grown into a facility with pressurized volume comparable to a 6-bedroom house. It hosted laboratories from multiple nations, sophisticated life support systems, recycling air and water, and solar arrays generating enough electricity to power the complex. Crews of 6 could live aboard comfortably for 6-month rotations, conducting experiments in biology, material science, fluid physics, and numerous other fields that benefited from the sustained microgravity environment. The station's greatest value might not have been its scientific output, substantial though that was, but rather the operational experience it provided. Keeping humans alive and healthy in orbit for months at a time required solving countless practical problems. How do you maintain equipment when replacement parts must be launched from Earth? How do you provide adequate nutrition with limited storage and no refrigeration? How do you maintain crew morale during long periods of isolation and confinement? How do you coordinate activities across multiple time zones with ground teams in different countries? The ISS became a proving ground for the operational aspects of spaceflight, generating knowledge that would be essential for any future missions beyond Earth orbit. With the shuttle retired in 2011, America temporarily lost the ability to launch its own astronauts. NASA relied entirely on Russian Soyuz spacecraft to transport crews to and from the ISS, a dependence that was both politically awkward and strategically concerning. This situation created opportunity for commercial companies that had been developing their own launch capabilities. SpaceX, founded by entrepreneur Elon Musk in 2002, successfully delivered cargo to the ISS, beginning in 2012 using its Dragon capsule and Falcon 9 rocket. Other companies developed their own systems, marking a shift from space access controlled exclusively by governments to a model where private companies competed to provide launch services. This commercialization of spaceflight had been advocated for decades by those who believed government programs were inherently inefficient and that market competition would drive innovation and reduce costs. The traditional aerospace contractors that had built spacecraft for government programs were now joined by newer companies with different approaches, willingness to take risks, and cultures borrowed from the technology industry rather than traditional aerospace. SpaceX in particular challenged established practices by developing reusable rockets that could land themselves after launch, dramatically reducing costs compared to expendable vehicles. By 2020, SpaceX was routinely launching and landing the same rocket boosters multiple times, finally achieving some of the reusability that the space shuttle had promised but never delivered economically. The ISS, meanwhile, continued operating well beyond its original planned lifetime. Modules designed for 15 years remained functional decades later. The station became the longest continuously inhabited human outpost beyond Earth, with crews present without interruption since November 2000. Astronauts and cosmonauts from dozens of nations visited, conducting research, maintaining systems, and occasionally venturing outside for spacewalks to repair or upgrade equipment. The station became almost routine, its presence in orbit taken for granted by a public that had once watched every launch with rapt attention. Yet that routine presence represented an extraordinary achievement. Humanity maintaining permanent occupation of space, learning to live and work beyond Earth as a normal, ongoing activity rather than a rare, spectacular event. While humans established permanent presence in low Earth orbit through space stations, robotic spacecraft ventured far beyond, exploring planets, moons, asteroids, and comets throughout the solar system. These unmanned missions, powered by rockets similar in principle to those carrying humans, but optimized for different purposes, expanded humanity's understanding of the cosmos in ways that would have astonished the early rocket pioneers. Without the need to support life or ensure safe return, robotic probes could travel farther, operate longer, and take risks that would be unacceptable with human crews aboard. The exploration of Mars became a particular focus, driven partly by scientific interest in whether life might once have existed there, and partly by the longer-term vision of Mars as a potential destination for human exploration. Early Mars missions in the 1960s and 70s, both American and Soviet, met with mixed success. Many spacecraft failed to reach Mars or malfunctioned upon arrival. But gradually, success rates improved as engineers learned from failures and refined their designs. In July 1976, Viking 1 touched down on Mars's surface, the first successful American landing on another planet. Its twin, Viking 2, followed weeks later. The Viking landers operated for years, far exceeding their design lifetimes, and transmitted thousands of images from the Martian surface. They analysed soil samples, measured atmospheric conditions, and conducted experiments searching for signs of microbial life. The life detection results were ambiguous, sparking debates that continued for decades. But the missions demonstrated that landing sophisticated scientific instruments on Mars was feasible. The rockets that launched these missions, Titan Centaur vehicles derived from military missile technology, performed flawlessly, delivering their payloads on trajectories requiring extraordinary precision across millions of miles. Mars exploration continued with increasing sophistication. The Pathfinder mission in 1997 delivered a small rover named Sojourner that could drive short distances from its lander, examining rocks and soil at multiple locations. The success of this comparatively inexpensive mission encouraged NASA to develop larger, more capable rovers. Spirit and Opportunity, twin rovers launched in 2003, were designed to operate for 90 days but functioned for years, exploring ancient lake beds and finding compelling evidence that liquid water had once flowed across Mars's surface. Opportunity remained operational for nearly 15 years, travelling almost 30 miles across Martian terrain before a massive dust storm finally silenced it in 2018. Curiosity, a rover the size of a small car, landed in 2012 and was still operating years later, drilling into rocks, analysing their composition, and gradually building a detailed picture of Mars's geological history. Its landing system was itself a marvel of engineering, a rocket-powered sky crane that hovered above the surface while lowering the rover on cables, a technique that seemed almost absurdly complex but worked perfectly. The rockets that powered this descent were small, precisely controlled engines burning hydrazine, descendants of the thrusters developed decades earlier for spacecraft maneuvering. Beyond Mars, robotic missions explored the outer solar system with remarkable success. The Voyager spacecraft, launched in 1977, took advantage of a rare planetary alignment to visit Jupiter, Saturn, Uranus, and Neptune on extended grand tours. Voyager 1, after passing Saturn in 1980, continued outward, and in 2012 became the first human-made object to enter interstellar space, leaving behind the Sun's influence. Both Voyagers carried golden records containing sounds and images from Earth, messages in bottles cast into the cosmic ocean, not with any realistic expectation they would ever be found, but as symbols of human aspiration. The Cassini mission to Saturn, arriving in 2004 after a 7-year journey, orbited the ringed planet for 13 years, studying its atmosphere, rings, and numerous moons. One of those moons, Enceladus, proved to harbour a subsurface ocean that erupts in geysers through cracks in its icy crust. Cassini flew through these geysers, sampling their composition and finding organic molecules, raising tantalizing questions about whether life might exist in that hidden ocean. The mission concluded in 2017 when Cassini, low on fuel and unable to continue, was deliberately plunged into Saturn's atmosphere to avoid any possibility of contaminating potentially habitable moons with Earth microbes. These distant missions required rockets capable of imparting enormous velocities to escape Earth's gravity well and travel to the outer planets. The Atlas and Titan rockets that launched most planetary missions were themselves evolved from Cold War ballistic missiles, their military origins repurposed for peaceful exploration. The launch vehicles had to be extraordinarily reliable since there was typically no opportunity to repair or retrieve a spacecraft once it left Earth orbit. A launch failure meant years of preparation and hundreds of millions of dollars lost, along with irreplaceable scientific opportunities. Closer to home, missions to asteroids and comets provided insights into the solar system's formation and composition. The Rosetta spacecraft, launched by the European Space Agency in 2004, travelled for 10 years to reach Comet 67P, then spent 2 years accompanying the comet as it approached the Sun. Rosetta deployed a small lander named Philae that touched down on the comet's surface, the first landing ever achieved on a comet. The mission revealed comets to be far more complex and diverse than previously imagined, with distinct geological features and unexpectedly hard surfaces in some areas. Sample return missions represented particularly ambitious undertakings, requiring spacecraft not only to reach distant targets, but to collect material and return it to Earth. Japan's Hayabusa spacecraft visited asteroid Itokawa, collected tiny particles from its surface, and returned them to Earth in 2010 after a 7-year journey plagued with technical problems that the mission team overcame through ingenuity and persistence. Hayabusa 2 repeated this achievement with asteroid Ryugu, returning samples in 2020. NASA's OSIRIS-REx mission visited asteroid Bennu, collected a substantial sample, and began its return journey, scheduled to deliver pristine asteroid material for laboratory analysis. These robotic explorers operated on minuscule budgets compared to human spaceflight programs, yet their scientific returns were enormous. They revealed worlds of astonishing diversity. Mercury with its enormous iron core, Venus with its crushing atmosphere and sulfuric acid clouds, Jupiter's moon Europa with an ocean larger than Earth's, hidden beneath kilometers of ice, Saturn's moon Titan with lakes of liquid methane. Each discovery raised new questions and identified new destinations worthy of exploration. The rockets launching these missions became increasingly sophisticated and reliable. Failures still occurred, but success rates improved dramatically compared to the early space age. Launch providers offered a range of vehicles optimized for different payload sizes and destinations. The Atlas V and Delta IV served as America's primary heavy-lift rockets for important missions. Europe's Ariane 5 launched both commercial satellites and scientific spacecraft. Russia continued operating its venerable Soyuz rocket, a design evolved continuously from the same basic architecture that had launched Sputnik decades earlier. Japan and China developed their own launch capabilities, joining the community of spacefaring nations. Yet despite this progress, a fundamental constraint remained. Chemical rockets, whether burning kerosene, liquid hydrogen, or hypergolic propellants, were limited by the energy available from chemical reactions. The exhaust velocities were bounded by physics, which meant reaching high velocities required enormous amounts of propellant. Tsiolkovsky's rocket equation remained as relevant as when he first derived it. The exponential relationship between velocity and propellant meant that missions to distant destinations required vehicles that were mostly fuel. For robotic probes, this was manageable, if expensive. For human missions beyond the Moon, it presented challenges that chemical rockets alone might not be able to overcome economically. The rockets that had carried humanity from Earth's surface to orbit and from orbit to the Moon were approaching their fundamental limitations. The 21st century brought renewed attention to the question that had motivated rocket pioneers from the beginning. Could humans travel beyond Earth orbit once again? And if so, where should they go? The International Space Station demonstrated that people could live in space for extended periods, and robotic missions had mapped potential destinations throughout the solar system. Yet the gap between what robots could do and what humans might accomplish remained vast, both technically and financially. Mars emerged as the most commonly discussed destination for human exploration. The planet was relatively close by cosmic standards, taking 6 to 9 months to reach depending on orbital alignment. It had an atmosphere, albeit thin, and substantial water ice at its poles and likely underground. Robotic missions had revealed a world with a complex geological history, ancient riverbeds, and conditions that might once have supported life. Most importantly, Mars offered the possibility of eventual human settlement, a concept that captured imaginations in ways that brief visits to barren moons could not. But travelling to Mars with humans aboard presented challenges far exceeding anything attempted during Apollo. The round trip would require at least 2 years, possibly 3, compared to the 8-day journey to the Moon and back. Everything needed for survival, every spare part, every contingency supply, would have to be carried from Earth or manufactured from Martian resources. A crew unable to return immediately if something went wrong would need redundant systems for life support, power, and propulsion. The radiation exposure during the journey would be significant, as travelers left behind Earth's protective magnetic field for months at a time. NASA studied various architectures for Mars missions throughout the early 2000s. Some proposals involved sending cargo ahead of the crew, pre-positioning supplies and equipment on the Martian surface before humans departed Earth. Others suggested assembling spacecraft in Earth orbit from components launched separately, avoiding the need for a single enormous rocket. Still others explored the possibility of manufacturing return propellant from Martian atmosphere and water, reducing what needed to be carried from Earth. Each approach had advantages and disadvantages, and each required technologies not yet fully developed. The rocket requirements for Mars missions were daunting. Even the mighty Saturn V that carried Apollo astronauts to the Moon would be inadequate for sending substantial payloads to Mars. Something larger was needed, capable of lifting 100 tons or more into orbit. NASA began developing the Space Launch System, a heavy-lift rocket using technology evolved from the Space Shuttle, including similar engines and solid rocket boosters. The SLS was designed to eventually launch 130 tons, more than the Saturn V, but still modest compared to some proposals. Meanwhile, SpaceX was developing its own vision for Mars exploration. Elon Musk, the company's founder, had stated from the beginning that his ultimate goal was enabling human settlement of Mars, making humanity a multi-planet species. SpaceX's approach differed fundamentally from NASA's traditional methods. Rather than building a rocket for a specific mission, they designed a fully reusable system called Starship that could be launched repeatedly with minimal refurbishment, dramatically reducing costs through high flight rates. Starship was enormous, standing nearly 400 feet tall when stacked atop its super heavy booster. The system was designed to carry 100 tons or more to Mars when refueled in orbit. The key to SpaceX's architecture was orbital refueling, launching tanker versions of Starship to transfer propellant to a Mars-bound vehicle, allowing it to depart with full tanks despite having consumed fuel reaching orbit. This approach was unprecedented in scale, requiring multiple launches for each Mars mission, but if successful would enable capabilities impossible with traditional expendable rockets. Development of Starship proceeded through rapid iteration, with prototypes built quickly, tested, and often destroyed during testing. This approach shocked traditional aerospace engineers accustomed to extensive analysis and conservative testing programs. SpaceX embraced failure as a learning tool, conducting tests that had substantial probability of explosive endings and using the data to improve subsequent designs. The company tested progressively larger prototypes, gradually validating technologies for landing giant rockets and rapidly reusing them. China also announced ambitious space plans, including intentions to land astronauts on the Moon and eventually reach Mars. The Chinese space program had advanced steadily over decades, achieving robotic lunar landings, returning samples from the Moon, and operating a space station. Unlike the Soviet program that preceded it, China's efforts were sustained and methodical, building capabilities incrementally without the dramatic peaks and valleys that characterized Cold War-era space competition. The new space race, if it could be called that, looked different from the Apollo-era competition. Multiple nations and even private companies were developing capabilities independently, pursuing overlapping but distinct goals. Cooperation continued alongside competition, with international partnerships on some projects, while others proceeded independently. The motivations were mixed: national prestige, scientific discovery, economic opportunity, and in some cases genuine belief that expanding beyond Earth was essential for humanity's long-term survival. nuclear propulsion emerged as a potential game-changing technology. Rockets using nuclear reactors to heat propellant could achieve much higher exhaust velocities than chemical rockets, making trips to Mars substantially faster and reducing radiation exposure. NASA and other agencies began developing small nuclear engines suitable for space use. The political and safety challenges of launching nuclear materials were significant, but the performance advantages were compelling enough to warrant continued research. The fundamental physics of rocketry had not changed since Tsiolkovsky first derived his equations. Reaching high velocities still required expelling mass at high speed, and the ratio between propellant and payload remained tyrannical. But engineering advances, improved materials, better manufacturing techniques, and especially reusability were gradually making what had seemed impossibly expensive potentially affordable. The question was shifting from whether humans could reach Mars to when they would go and who would get there first. Public interest in space exploration had fluctuated over decades. The Apollo landings captivated global attention, but interest waned as missions became routine. Shuttle launches barely made the news unless something went wrong. The ISS operated in relative obscurity despite being humanity's outpost in space. Yet something was changing. New generations who had never experienced Apollo were becoming excited about space again, inspired by images from Mars rovers, by spectacular rocket landings, and by the prospect that space might become accessible not just to government astronauts, but eventually to ordinary people. The rockets being developed in the early 21st century carried not just payloads, but renewed aspirations. As rocket technology matured and spaceflight became increasingly routine, attention began shifting from how to reach orbit to what could be accomplished once there. The economic potential of space, long discussed theoretically, started becoming practical reality. Communications satellites had been commercially viable since the 1960s, but new opportunities emerged as launch costs declined and capabilities expanded. The space economy was taking shape, driven not by governments pursuing strategic objectives, but by companies seeking profit and competitive advantage. The most visible aspect of this commercialization was the satellite industry. Thousands of satellites orbited Earth by the early 21st century, providing services that had become essential to modern civilization. Communication satellites relayed telephone calls, television broadcasts, and internet data across continents and oceans. Navigation satellites enabled precise positioning for everything from farming equipment to smartphones. Earth observation satellites monitored weather, tracked environmental changes, assisted disaster response, and provided imagery for countless applications from urban planning to military intelligence. Launching these satellites had traditionally been expensive, limiting the market to large government and corporate customers who could afford missions costing tens or hundreds of millions of dollars. But as launch costs decreased, new business models became viable. Companies began proposing constellations of hundreds or thousands of small satellites working together to provide services that previously required large, expensive individual spacecraft. These small satellites, some weighing just a few pounds, could be manufactured relatively cheaply and launched many at a time, sharing the cost of a single rocket. SpaceX's Starlink constellation exemplified this approach. The company began launching satellites in 2019 with the goal of providing global internet coverage from space. Each satellite was roughly the size of an office desk and weighed about 500 pounds. Falcon 9 rockets carried up to 60 satellites per launch, releasing them into orbit where they used onboard propulsion to reach their operational positions. By the early 2020s, thousands of Starlink satellites orbited Earth, providing internet service to remote areas and generating revenue that helped fund SpaceX's broader ambitions. Other companies pursued similar concepts. OneWeb launched its own constellation for internet service. Amazon announced plans for thousands of satellites. China began developing competing systems. The proliferation of satellites raised concerns about orbital congestion and space debris. Each satellite eventually became a piece of junk when it stopped functioning, and collisions between defunct satellites could create cascading clouds of debris that might render some orbital regions unusable. Regulations and coordination mechanisms struggled to keep pace with the rapid expansion of commercial space activity. Beyond communications and Earth observation, more speculative economic opportunities attracted investment and attention. Asteroid mining companies proposed extracting valuable materials from near-Earth asteroids, where metals and water might exist in concentrations far exceeding typical ore on Earth. The engineering challenges were formidable and the economics uncertain, but the concept was serious enough that major investors provided funding. Launch costs would need to decrease substantially before asteroid mining became profitable, but the trajectory of rocket technology suggested this might eventually be achievable. Space tourism represented another emerging market. For decades, the only people who reached space were professional astronauts selected through rigorous competition and trained extensively. But as launch capabilities improved and costs declined, companies began offering space experiences to paying customers. Russia had allowed wealthy individuals to visit the ISS aboard Soyuz spacecraft, charging tens of millions of dollars per seat. These orbital tourists received training and participated in station activities during week-long visits. New companies proposed making space tourism more accessible. Blue Origin, founded by Amazon's Jeff Bezos, developed the New Shepard vehicle for suborbital flights that would take passengers just past the boundary of space for a few minutes of weightlessness before returning to Earth. Virgin Galactic pursued a similar market with a rocket-powered spaceplane. These suborbital experiences wouldn't achieve orbit, but they would provide the weightlessness and views that defined the astronaut experience. The tickets cost hundreds of thousands of dollars initially, but companies projected that prices would decrease as operations scaled up. SpaceX went further, announcing plans to fly private citizens on orbital missions and eventually around the Moon. The first purely commercial orbital missions launched in the early 2020s, carrying civilians who had purchased entire flights. These missions demonstrated that accessing space no longer required government sponsorship, though it still required substantial wealth. The long-term vision, articulated by multiple companies, was that space tourism would eventually become affordable for middle-class customers, similar to how air travel evolved from exclusive luxury to routine transportation. Manufacturing in space attracted interest as launch costs decreased. The microgravity environment enabled production of materials and pharmaceuticals difficult or impossible to make on Earth. Fiber optic cables grown in weightlessness could achieve higher purity. Certain protein crystals useful for drug development formed better structures in microgravity. The market for these products was initially small, but research continued on the ISS and on free-flying manufacturing platforms. The regulatory and legal frameworks governing space activity struggled to adapt to commercial expansion. International treaties from the 1960s established that nations couldn't claim sovereignty over celestial bodies and remained responsible for their citizens' space activities. But these treaties were drafted when only governments operated in space. Questions about property rights, resource extraction, liability for accidents, and jurisdiction over private activities in orbit lacked clear answers. Some nations began developing national space laws to fill these gaps, but international coordination remained incomplete. solar power from space emerged as a potential solution to Earth's energy needs. Satellites could collect sunlight continuously without atmospheric interference or nighttime interruptions, then beam power to Earth using microwaves or lasers. The concept had been studied since the 1970s, but the enormous upfront costs of launching massive solar arrays made it economically impractical. However, projections of dramatically reduced launch costs made the concept worth reconsidering. If rockets could deliver cargo to orbit for hundreds rather than thousands of dollars per kilogram, space-based solar power might compete with terrestrial alternatives. All these emerging activities depended fundamentally on rocket technology continuing to improve and costs continuing to decline. The relationship was reciprocal. New economic opportunities justified investment in better rockets, while better rockets enabled new opportunities. This virtuous cycle, if sustained, could transform humanity's relationship with space from occasional visits by small numbers of highly trained specialists to routine operations involving thousands of people and generating substantial economic value. The rockets themselves continued evolving. Methane emerged as a preferred fuel for some applications, burning cleaner than kerosene and easier to handle than hydrogen. Engines became more efficient and reliable through improved materials and manufacturing techniques. Reusability, once theoretical, became standard for some vehicles. The distinction between government and commercial space programs blurred as NASA and other agencies increasingly purchased launch services from private providers rather than operating their own vehicles. Space was becoming, incrementally but unmistakably, a domain of commerce and industry, alongside exploration and scientific research. The evolution of rocket technology over more than a century had followed a path from crude gunpowder tubes to sophisticated machines capable of placing humans and cargo into orbit with reasonable reliability. Yet for all this progress, the fundamental principle remained unchanged. Rockets worked by expelling mass in one direction to accelerate in the other. This simple truth, first demonstrated by Chinese fire arrows and later formalized in Newton's laws, imposed constraints that even the most advanced engineering could not eliminate entirely. Every kilogram lifted to orbit required many kilograms of propellant, and this ratio grew worse for missions beyond Earth orbit. Engineers and scientists had long recognized that chemical rockets, while sufficient for reaching orbit and perhaps the moon, were poorly suited for deeper space exploration. The energy available from burning fuel was fundamentally limited by chemistry. Hydrogen and oxygen combustion, the most energetic commonly used chemical reaction, produced exhaust velocities around 4.5 kilometers per second. This was enough to reach orbit if rocket design was efficient, but barely adequate for interplanetary missions, and wholly insufficient for reaching the stars within human lifetimes. Nuclear propulsion offered one path beyond chemical limitations. A nuclear reactor could heat propellant to much higher temperatures than chemical combustion, producing exhaust velocities 2 or 3 times greater. This translated to missions requiring far less propellant or reaching destinations much faster. NASA and other agencies had studied nuclear rockets since the 1950s. Ground tests of nuclear engines in the 1960s demonstrated the concept worked, but political concerns about launching radioactive materials and the end of Apollo eliminated funding for continued development. By the early 21st century, interest in nuclear propulsion revived as Mars missions shifted from theoretical studies to serious planning. The trip to Mars could be cut from 6 or 9 months to perhaps 3 months using nuclear thermal rockets. Shorter travel times meant less radiation exposure, less time for equipment to fail, and reduced psychological stress on crews. NASA began developing small nuclear reactors, specifically designed for space propulsion, addressing safety concerns through careful design and testing protocols. Electric propulsion represented a different approach to efficiency. Ion engines and similar technologies used electricity to accelerate propellant to extremely high velocities, far exceeding what chemical or nuclear thermal rockets could achieve. The catch was that thrust remained tiny, comparable to the weight of a sheet of paper. Electric propulsion couldn't lift anything off Earth's surface, but once in space, these engines could operate continuously for months or years, gradually building up enormous velocities. Robotic missions to distant planets increasingly used electric propulsion for the efficiency it provided. Solar sails offered propulsion without expelling any mass at all. These vast mirror-bright sheets captured momentum from sunlight itself. The force was incredibly weak, but it was continuous and required no propellant. Several experimental spacecraft demonstrated solar sail technology, unfurling gossamer structures in orbit and using sunlight pressure to change their orbits. For certain missions, particularly those staying in the inner solar system where sunlight was strong, solar sails might eventually prove useful. They would never replace rockets for most purposes, but they added options to the toolkit of space propulsion. More speculative concepts existed largely in theoretical form. Fusion rockets, burning the same reaction that powered the sun, could theoretically reach exhaust velocities far exceeding any chemical or fission system. The challenge was that controlled fusion remained elusive despite decades of research on Earth. Creating the conditions for fusion was one thing. Doing so in a compact, reliable rocket engine was vastly more difficult. Still, if fusion power ever became practical for terrestrial use, space propulsion would likely follow. Antimatter represented the ultimate rocket fuel from a physics perspective. When matter and antimatter met, they annihilated completely, converting mass to energy with perfect efficiency according to Einstein's famous equation. No other reaction could release more energy per unit mass. The problems were practical rather than theoretical. Antimatter didn't exist naturally in useful quantities and had to be manufactured particle by particle in enormous accelerators at tremendous cost. Storing antimatter without it touching normal matter and annihilating was extraordinarily difficult. The amounts needed for a rocket would be far beyond anything currently producible. Antimatter propulsion remained firmly in the realm of speculation, though physicists continued exploring the concept. For the foreseeable future, chemical rockets would remain the workhorses of spaceflight, lifting payloads from Earth's surface to orbit where other propulsion methods might take over for the next leg of a journey. The tyranny of the rocket equation meant that reaching orbit required enormous energy expenditure, and chemistry provided a compact, reliable way to store and release that energy. Improvements would continue, engines becoming more efficient, structures becoming lighter, manufacturing becoming cheaper, but revolutionary breakthroughs in chemical propulsion were unlikely. The chemistry was well understood, and performance was approaching theoretical limits. The real revolution, if it came, would be in reusability and operational efficiency. Rockets didn't need to perform dramatically better if they could be used repeatedly with minimal refurbishment between flights. An airplane wasn't thrown away after each flight, and there was no fundamental reason rockets had to be. SpaceX had proven that rocket boosters could land themselves and fly again. Other companies were pursuing similar approaches. If rockets could operate more like aircraft, launching frequently with rapid turnaround and low maintenance costs, then space access would become affordable, even without exotic propulsion technologies. Launch systems beyond rockets also attracted attention. Space elevators, massive cables stretching from Earth's surface to orbit, had been proposed as ways to lift cargo without rockets at all. The concept was theoretically sound, but required materials far stronger than anything currently available. Carbon nanotubes might eventually provide sufficient strength, but manufacturing cables thousands of miles long from such materials remained beyond current capabilities. Space elevators, if ever built, would transform access to space, but they belong to a more distant future. Railguns and similar electromagnetic launch systems offered another alternative. These devices used powerful magnets to accelerate payloads to orbital velocities along tracks, potentially launching cargo without chemical propellants at all. The accelerations would be far too intense for human passengers, but satellites and supplies might be launched this way if the engineering challenges could be overcome. Several research programs explored the concept, building small-scale demonstrators and studying what would be required for an operational system. Yet for all the speculation about advanced propulsion and alternative launch methods, the immediate future of spaceflight would be shaped by incremental improvements to existing technology. Better materials, more efficient engines, improved manufacturing, and especially reusability would make space more accessible without requiring revolutionary breakthroughs. The rockets of the 2020s looked similar to those from previous decades, but performed better and cost less to operate. This trend would likely continue, gradually opening space to more activities and more participants. The fundamental challenge remained unchanged from Tsiolkovsky's time. Leaving Earth's gravity required enormous energy, and that energy had to come from somewhere. Rockets provided a solution that worked, transforming chemical energy into kinetic energy efficiently enough to reach orbit. Better solutions might eventually emerge, but rockets had carried humanity from its first tentative steps into space to routine operations in orbit and visions of settlement beyond Earth. Whatever came next would build on this foundation. Beyond the practical concerns of propulsion systems and orbital mechanics, space exploration raised profound questions about humanity's future and place in the cosmos. The rockets that had begun as weapons and evolved into vehicles for exploration were enabling a transformation in how humans understood themselves and their relationship to Earth. For the first time in history, leaving the planet was not just imaginative fiction, but practical possibility, at least for some. And this realization carried implications that extended far beyond technology. The images returned by spacecraft, particularly those showing Earth from space, had unexpected emotional and philosophical impact. The photographs taken by Apollo astronauts showing Earth as a fragile blue sphere against the blackness of space became some of the most influential images ever captured. They helped catalyze environmental movements by making viscerally clear that Earth was an isolated, finite world without borders visible from space. The perspective from orbit revealed a planet that was home to all humanity, a single interconnected system whose atmosphere and oceans recognized no political boundaries. This overview effect, as some called it, was reported by many astronauts who had seen Earth from space. Something about the direct experience of looking back at the planet from orbit or beyond seemed to produce a shift in consciousness, an understanding that the divisions between nations and peoples were human constructs, while the planet itself was unified and precious. Whether this perspective could influence humanity's behavior remained uncertain, but the testimony of those who had experienced it was remarkably consistent across cultures and nationalities. The prospect of becoming a multi-planet species, of establishing permanent human presence beyond Earth, raised questions about why such expansion should occur and what it might mean. Some advocates emphasize survival, arguing that humanity concentrated on a single planet remained vulnerable to catastrophes ranging from asteroid impacts to nuclear war to environmental collapse. Establishing self-sufficient settlements elsewhere would ensure that some branch of human civilization survived, even if Earth suffered disaster. This argument appealed to those who thought in terms of risk management and species-level survival. Others focused on resources and opportunity. The solar system contained vastly more material and energy than existed on Earth's surface. Asteroids held metals in quantities that could supply industrial civilization for millennia. The Moon possessed materials useful for construction and fuel production. Mars offered a world that might be slowly transformed over centuries into something more Earth-like, a process called terraforming that remained entirely theoretical but captured imaginations. From this perspective, expanding into space represented the next chapter in humanity's story of growth and exploration. Critics questioned whether space expansion was appropriate when serious problems remained unsolved on Earth. The resources devoted to space programs, they argued, might be better spent addressing poverty, disease, environmental degradation, and social inequality. Space exploration was portrayed as expensive distraction from urgent terrestrial concerns, a form of escapism that allowed the wealthy and powerful to fantasize about leaving Earth's problems behind rather than solving them. This critique had force, particularly when space programs consumed public funds that might otherwise support social services. The debate often talked past itself because participants held fundamentally different assumptions about human nature and civilization's trajectory. Those skeptical of space expansion tended to view it as optional, a luxury that should be deferred until more pressing needs were met. Space advocates often saw expansion as inevitable and necessary, something that would happen eventually and might as well begin sooner. Neither position could be definitively proved, making the argument as much about values and vision as about practical considerations. The ethical dimensions of space settlement raised difficult questions. Who would go, and who would decide? If space colonies were established, would they remain under Earth's authority or become independent? What responsibilities would settlers have toward any life that might exist elsewhere, even in microbial form? The discovery of living organisms on Mars or Europa would profoundly complicate plans to exploit those worlds' resources. Even if no life existed, some argued that pristine environments had intrinsic value, deserving protection regardless of economic or strategic considerations. The economics of space development remained uncertain despite increasing commercial activity. Whether the investments being made would generate returns sufficient to justify continued expansion was genuinely unclear. Communication satellites were profitable, and Earth observation had obvious value, but whether mining asteroids or manufacturing in orbit would ever be economically viable remained unproven. The history of frontiers on Earth offered mixed lessons. Some frontier regions had generated enormous wealth, while others consumed resources for generations before providing returns if they ever did. Cultural impact of space exploration was undeniable, even if its ultimate significance remained debatable. The space age had inspired countless people to pursue careers in science and engineering. The technologies developed for space programs had applications far beyond rocketry, from improved materials to better computers to medical devices. The images and knowledge returned by space missions had expanded human understanding of the cosmos and our place within it. Whether these contributions justified the costs was a question without objective answer, depending on how one valued knowledge, inspiration, and long-term potential versus immediate practical benefits. Literature, film, and popular culture had been shaped profoundly by space exploration. Science fiction, which had inspired many of the pioneers who developed rockets, now drew on real achievements to imagine futures both utopian and dystopian. The iconography of spaceflight, from sleek rockets to suited astronauts to views of Earth from orbit, became part of global visual culture. For many people, particularly younger generations, the possibility of space travel represented hope that humanity's future held more than decline and limitation. Indigenous perspectives on space exploration sometimes offered alternatives to the dominant narratives of conquest and expansion. Some indigenous thinkers emphasized that humans had responsibilities to Earth that should be fulfilled before seeking other worlds. Others pointed out that the language of space exploration often echoed colonial rhetoric, with terms like frontier and settlement carrying troubling historical associations. These voices reminded space advocates that how expansion proceeded mattered as much as whether it occurred. The rockets themselves, the machines that made space accessible, carried no inherent ideology. They were tools that could serve various purposes and values. Whether they ultimately contributed to human flourishing or became instruments of new forms of inequality and exploitation would depend on choices made by societies and individuals in coming decades. The technology had arrived. What humanity would do with it remained to be determined. As the 21st century progressed, the landscape of spaceflight continued evolving in directions that would have surprised earlier generations. China's space program emerged as a major force, methodically building capabilities through sustained investment and long-term planning. After achieving robotic lunar landings and sample returns, China announced intentions to establish a permanent lunar base in cooperation with Russia and other nations. This base would serve as a research station and potentially a staging point for deeper space missions. The Chinese approach differed from the rapid, risk-accepting methods pioneered by SpaceX. Chinese missions proceeded carefully, with extensive ground testing and conservative designs that prioritized reliability over speed of development. By the mid-2020s, China had launched its own space station, conducted multiple lunar missions, and was developing heavy-lift rockets comparable to anything America or Russia possessed. International cooperation expanded even as national competition continued. The Artemis program, led by NASA but involving space agencies from Europe, Japan, Canada, and other nations, aimed to return humans to the moon and establish sustainable presence there. Unlike Apollo, which planted flags and departed, Artemis envisioned permanent infrastructure, habitats where astronauts could live for months, rovers for extended exploration, and systems to extract water ice from permanently shadowed craters near the lunar poles. Commercial space stations represented the next evolution beyond the ISS. Companies announced plans to build private orbital facilities that would host research, manufacturing, and tourism. NASA planned to retire the ISS in the late 2020s and transition to purchasing services from commercial providers rather than operating its own station. This shift reflected confidence that the private sector could reliably provide orbital infrastructure. Small nations traditionally excluded from spaceflight began developing their own capabilities. The United Arab Emirates successfully placed a probe in Mars orbit. India landed a spacecraft near the lunar South Pole. Private companies in various countries competed to offer launch services. The club of spacefaring entities was expanding rapidly, democratizing access to a domain once reserved for superpowers. The regulatory challenges of increasing space activity grew more complex. Space debris remained a serious concern, with defunct satellites and fragments from collisions posing risks to functioning spacecraft. Earth observation from space became increasingly sophisticated, with satellite imagery offering resolution fine enough to identify individual vehicles. This capability had obvious applications, but raised privacy concerns that different nations addressed with different policies. Mars remained the primary focus for human exploration beyond the Moon. Multiple mission architectures were refined and compared. Some involved stopping at the moon first to test technologies. Others proposed direct missions from Earth to Mars. No consensus emerged on the best approach, and different nations and organizations pursued different strategies. The question of when humans would reach Mars attracted endless speculation, with estimates ranging from the early 2030s to the 2040s or beyond. Standing at this moment in history, with routine access to orbit achieved and expeditions to other worlds under serious consideration, the journey from ancient fire arrows to modern spacecraft represents one of humanity's most remarkable technological achievements. What began as crude weapons evolved into instruments of exploration, commerce, and potentially transformation. The basic physics that Tsiolkovsky articulated over a century ago remains unchanged. Yet within these fundamental constraints, enormous progress has occurred through better materials, improved efficiency, and especially the advent of reusability. The rockets launching today are evolutionary descendants of the V2, but they are as different from that ancestor as a modern automobile is from an early horseless carriage. They are more powerful, more reliable, more efficient, and increasingly more affordable. The technologies required to achieve this would have seemed like magic to earlier rocket engineers. Looking forward, the next few decades will likely see continued incremental improvement rather than revolutionary breakthroughs. Chemical rockets will remain the primary means of reaching orbit because they provide a good balance of energy density, controllability, and reliability. Reusability will become standard, driving down costs and enabling higher flight rates. Access to space will become more routine and available to a broader range of users. Human presence beyond Earth will probably expand slowly at first, then more rapidly as infrastructure develops. The Moon will likely host permanent research stations before mid-century, serving as both scientific outposts and training grounds for deeper space missions. Mars will eventually receive human visitors, though exactly when remains uncertain. These early Mars missions will be tentative and expensive, testing whether humans can survive and function effectively on another planet. The broader impact of space development on human civilization remains unpredictable. Optimists envision a future where resources from asteroids supplement Earth's materials, where manufacturing moves to orbit, and where eventually substantial numbers of people live beyond Earth. Skeptics question whether these visions are economically feasible. Both perspectives contain truth. Space development will almost certainly proceed, driven by scientific curiosity, strategic competition, and economic opportunity, but likely more slowly than enthusiasts hope. The cultural legacy of the space age extends beyond practical achievements. The view of Earth from space changed how humans perceive their home planet. The realization that we can leave Earth altered our understanding of what is possible. The knowledge gained from exploring other worlds enriched science and inspired generations. These intangible benefits resist quantification but matter nonetheless. The rockets themselves remain impressive machines, among the most complex and powerful devices humans have ever built. Watching a heavy lift rocket launch, feeling the ground shake, hearing the thunder of engines, witnessing something weighing thousands of tons rise against gravity, one cannot help but feel awe at what human ingenuity can accomplish. As evening draws toward night, consider that overhead, moving silently across the darkness, spacecraft and satellites trace paths around the world. Some carry astronauts living in orbit. Others relay communications, monitor weather, or observe Earth and space. All reached their destinations aboard rockets, descendants of those ancient fire arrows, evolved through generations into vehicles that routinely accomplish what our ancestors would have considered miracles. The story continues. New rockets are being designed. New missions are being planned. New destinations beckon. Whether humanity's future lies primarily on Earth or increasingly among the stars remains to be written. But the rockets that made leaving Earth possible represent a pivotal chapter in human history, the moment when our species gained the capability to venture beyond its birthplace. That capability, once achieved, cannot be unlearned. The journey from fire arrows to modern spacecraft has taken centuries. It has been possible because people throughout history looked upward, wondered what lay beyond the sky, and worked to build machines that could take them there. The rockets are their legacy and our inheritance, tools for reaching toward possibilities that previous generations could only dream about. Rest now, knowing that above, the work continues, and tomorrow brings new opportunities for discovery.